Hello, hello, hello. We're in my car today at the Frozen Chosen, Indianapolis, Indiana, waiting for great clips. I wonder why. Oh well, it's time to trim it down a little bit. Getting a little unruly at work. So, time to freshen up. Next time you see me, I'll be a new man. Well, today we're looking at the present progress of my 4 million digit computation of the MRB constant. We're at a wonderful 628,736 iterations. Let's compute or calculate. I use the two terms synonymously, even though they're not really synonymous. Uh, you can write me, though, and tell me and correct me and give me some advice on when to use one and when to use the other. I'd appreciate that. Not that I'd follow it, but I'd appreciate it. Let's see if I got a calculator of some sort open. Now I'll open one. Calculator. Okay. Let's see. Now I can do this. Edit, paste, or Control V. That's the present number of iterations. Let's go back to the required iterations. There's the program, by the way. I'll go over it in detail in a future program. There's iterations required. Let's use the iterations that it will actually stop with, because although it'll have more than 4 million digits by then, um, it won't stop computing until then. So let's go back to that calculator. Divided by Control V times 100%. Okay, it appears that we're 11.8% of the way done. We could calculate how long it will take, but I have the program already doing that for us. So let's look at that. My Digital Storm PC here. It tells us how long it will take, approximately. It will finish Wednesday, January the 16th at 1:51 and 52 seconds in the AM. So, I haven't got any remarks on whether you understood my definition of the MRB constant. That is when you take -1 plus the square root of 2 minus the cube root of 3 plus a fourth root of 4 and keep on going to a large even number. And when you stop at that large even number, like a million or a billion or a trillion or quadrillion or Googleplex, you get an approximation of the MRB constant. By the way, stopping at a Google only gives you around 100 actual digits of the MRB constant. That's how slow that series is to converge. So you use, to compute digits of the MRB constant, you really need to use a program that employs acceleration methods. This program was originally written by the late Richard Crandall, and I've been working on it since 2012. I've made some decent improvements on it, about tripled the speed of it since then, depending on the computer. On my computer, I have. Maybe someone else's, it might not be quite that much of an improvement. But I've been working on it for years and years. And I don't know how much I want to get in detail about it today, but it uses a program, an algorithm by Cohen and others for acceleration of convergence. And in there, you find a D and an S. And the sum of your a sub n's, your sum of the negative 1 to the power of n times your a sub n's equals negative s over d. I sped up the d computation where it's right here. Chebyshev t of n comma 3. Let's make that a little one line. And then the s is computed by an iteration, a set of iterations. That's what I mean when I say we got iterations required or iterations done. Um, you'll see here that the S um, right here S is being iterated, and each time it's adding to itself what's called a C tab and the X vowels minus 1. The X vowels are the roots, uh, negative 1, the square root of 2, the cube root of 3, the fourth root of 4, and they're minus 1. Each one. So you got negative 1 minus 1, you got the square root of 2 minus 1, you got the cube root of 3 minus 1, you got the fourth root of 4 minus 1, and that gives you a convergence series where I mentioned before when you're computing the MRB constant that you have to stop at an even number to get the MRB constant. If you stop at an odd number, you get the MRB constant minus 1. But if you subtract 1 from each term, you automatically get the MRB constant whether you stop at an even number or odd number, so it's a convergence series. And C tab is the part of the Cohen algorithm that causes the speed up in the computation for each iteration. It speeds it up from a from simple addition series, negative 1 plus the square root of 2, to, let's see here, how can I say it? Instead of a logarithmic convergence speed, it speeds it up to nearly linear. So at least that's what I found out. The computer went to sleep there almost. So anyway, I'll discuss it more in detail later, and you can find out more by looking at my program and searching convergence of alternating series. Add Cohen's name; he's one of the authors, the one I remember. There were 3 authors though, and it's pretty well used in accelerating convergence series by mathematicians, real mathematicians, not just amateurs like me. So anyway, we've had a long session today, And we said the computation was 11.8% done. By the way, yesterday we saw that it was 10.2% done. So 11.8 minus 10.2 is 1.6 or so. 1.6% of the computation right now is being completed each day. Well, I'll let you figure out the rest from there. This is Marvin Burns, Marvin Ray Burns, if you want to search me on the internet, signing off.